So I will introduce the next speaker of this session to you, and this is Hassam Rassouli from the University of Hertfordshire. He has a master in pharmacy and is currently carrying out his PhD in the EPSRC Center for Doctoral Training in Aerosol Science. He was awarded the best clinical student during his undergrad studies, and he developed an interest in researching mental health and alternative routes for targeted and systemic drug delivery. So currently, his work focuses on the development of smart thermoresponsive and shear thinning polymeric formulations. And he'll talk to us about computational approach for estimation of formulation-dependent fluid dynamics in a nasal delivery device.
Thanks a lot, and you pronounced my name perfectly, by the way. So yeah, as Regina said, I'm giving a talk on computational approaches for understanding fluid dynamics in nasal spray devices. Very quick background initially, as most of you have seen nasal spray pumps that look something like the ones behind me here, they rely on shear rates generated during actuation to actually form fine droplets from the liquid bulk, and that's what we call the spray plume. And that shear rates, generally speaking, in most nasal spray devices is in the region of 10 to the 5 reciprocal seconds. What problem this causes is that the high viscosity formulations that experience lower shear rates in nasal spray pumps would not be sprayable in these traditional nasal spray pumps. And that is due to the fact that they would form a jet. Therefore, we cannot use too much viscosity modifiers that would in turn be mucoadhesive polymers, and as such, we're reducing the retention time in the nasal cavity for every formulation that we have. So what is the motivation for what we're doing? We now know that newer generation of nasal drug delivery devices, such as Nasadose, Bestpac's proprietary nasal spray system, uses a much more improved flow path and actuation mechanism, which improves the shear rates that we are able to generate during actuation. And what this allows us to do is actually go back to the drawing board and be able to spray those viscous materials that previously we would have thought would be impossible. So the aims of our study, we aim to develop a computational fluid dynamic model that is able to do three main things. Firstly, study the flow of Newtonian and non-Newtonian fluids in the Nasadose device. Secondly, understand the shear rate of Newtonian and non-Newtonian fluids in the Nasadose device. And finally, study the favorable rheological properties for spray generation in the Nasadose device. Moving on to the bit of my methodology here, we initially looked at rheology of some formulation, and that was 50% polyethylene glycol 4000. This was done at shear rates ranging from 0.01 reciprocal seconds to 10 reciprocal seconds, and was measured using a rotational rheometer. Moving on to the geometry and boundary condition, these are key things for anyone that knows how CFD works. And what we did here was we developed a computational aided design based on the Nasadose device. What we did was developed a model that includes the internal drug flow path, including a vial system connecting to a needle and then leading on to the soil chamber and the atomizer itself. As you can see on the left-hand side, we have a velocity inlet, which is a constant inlet velocity moving in the fluid at the same velocity over time. On the right-hand side, we have a pressure outlet over here. And finally, everything else was set as a non-slip wall. Moving on to the physical models, possibly the most important thing in a CFD model, and we use two main ones, the volume of fluid, which is simply a Eulerian multiphase approach. It allows us to locate and track the liquid-air interface, as you can see in a lovely picture I've stolen from our good old friend Wikipedia. It's very good at giving us the fluid flow and also understanding the liquid-air interface interactions, such as the shear rate that I spoke about before. And finally, we looked at the K-omega shear stress transport model, which is a very good model for understanding very low turbulence to kind of the transitional flow regions in a flow path. And based on our Reynolds number, we assume that that would be good. Moving on to the results. So initially, rheology. This has been looked at previously, but Deyao et al. Did a very good job. They looked at 2 different nasal pumps for spraying various viscosity of formulations. And what they found was that with the traditional nasal spray pumps, they were only able to spray low viscosity formulations in the region of 0.004 Pascal seconds. The high viscosity pump, on the other hand, improved it to 0.02 Pascal seconds. And what we tried to do was really just one-up them and go slightly higher. We went to a formulation where the infinite shear viscosity is at approximately 0.03 Pascal seconds. That would be viscosity at relatively high shear rates. And what we then did was input these rheological data onto a power law model and a cross model. These equations would then be inputted into our CFD simulations to give us some good-looking data, which I'm just going to go through now. Firstly, fluid flow. So fluid flow in the needle initially, you can see that they both look very similar for both formulations. They're both non-parabolic flows, which is understandable due to the high turbulence that I spoke about before. However, moving on to the swirl chamber, it gets quite interesting. We can see that for both formulations, we are able to generate an air core, and over here, for both formulations. But the difference between the difference between the 2 formulations is that we were able to generate this air core a lot quicker with the water formulation, and also it's much more apparent starting from the base of the swirl chamber. Looking at it for polyethylene glycol, we can see that it's a tiny bit of an air core developed there from the swirl chamber, and it takes about double the time at 13 milliseconds to develop. So we can assume that we're still getting the spray generation with these viscous fluids. However, the device is slightly struggling, taking a bit longer for it to happen as well. Moving on to the velocity profile. Velocity is very important because that's what gives the energy for the fluid bulk to actually break up to the finer droplets. And we can see that, interestingly, for both formulations, velocity is relatively high. Higher for water, and that's expected because of the lower viscosity at about 70 meters per second. But with polyethylene glycol, we're still getting velocity at the air core that is quite close to 50 meters per second. That gives us favorable results that we can assume we are actually getting some spray generation here. Finally, looking at the strain rates, we can see that the strain rate for polyethylene glycol at the needles unexpectedly higher than the low viscosity formulation. However, this is expected because we actually used a constant inlet velocity. If we do use a variable inlet velocity, this would change. And looking at the shear rates at the swirl chamber, actually, we get some very good looking data. So we can see that at the air core, we're getting these strips of very high shear rates at the liquid air interface. And what that shows us is that we are getting the energy required for that breakup of the fluid bulk to finer droplets. Looking at it for polyethylene glycol's case, we can see that the shear rate is lower compared to water, and that's expected because of the higher viscosity. However, it's still at about 1.42 to the power of 6, 2 times 10 to the power of 6 reciprocal seconds. That's at least an order of magnitude over what we expected from traditional spray pumps. So we can confidently say that these formulations would spray. So what does all this mean in clinical use? Because I've given you a lot of assumptions, and I don't want to go through this over a long time because my good friend Abhishek is actually having a poster on Poster 103. So do go and talk to him if you're interested. But the only statement I'd like to make is that it is absolutely remarkable that we are spraying these formulations from a nasal spray device, given that our high viscosity emulsion formulation is 900 times more viscous than water. If I didn't know any better, I would say it's magic, but no, it's just the Nasodose doing its thing. Quick conclusion, Nasodose is able to generate very high shear rates and velocities, which give us a good estimation that we are going to be able to spray viscous and non-viscous formulations. And secondly, this model as a whole allows formulation scientists and and device manufacturers the ability to do two very important things and quite rapidly. It allows us to estimate wide range of formulations and their sprayability in the nasal dose device. And also it will allow us to, if one specific formulation is all you need, you will be able to fine tune your device parameters to improve the sprayability of that formulation. Finally, I'd just like to take some time to acknowledge all the lovely people and organizations who've made this research possible, namely Dara Manane, Michael Cook, Adam Gibbons, and Sabrina Fallon. And yeah, the UHHPC has been great, the EPSRC for funding it, and I can't say anything bad about the Center for Doctoral Training in Aerosol Science. They are great, they're doing great things. And importantly, thank the DDL committee for giving me this opportunity and all of you for actually taking the time to listen to me. I'll be happy to take any questions.
Thank you, Hassam, for this very nice talk. Are there any questions? Go ahead.
Hey, really interesting talk. Thank you. It's Will Ganley from Nanopharm. So I'm interested in the time dependence. So you mentioned that you had static inlet velocity,
Yes.
and you input the cross and the power law models, but you didn't include any thixotropy, any time dependence to the shear rate changes. So when you actuate a nasal device, I guess there's some change in the velocity and the stresses in the device as you're pressing it. Is that right? And I just wonder if you were to include those things, would you see difference?
So there would be some changes in following actuation from the velocity inlet, and that's part of the ongoing work. We are trying to input that variable inlet velocity to be able to become more clinically relevant as well. So yes, you're absolutely right, and that is part of the ongoing work.
Any teasers on what that's looking like?
Maybe the next DDL.
Okay, thank you.
Hey, I wonder if you've considered surface tension as part of the Rayleigh sort of Taylor instability of the droplet formulation in your model?
We have considered the surface tension in these simulations. They do have a bit of an effect. However, the biggest effect of surface tension would actually be if we looked at what happens after the nozzle, because surface tension is quite important for actually the fine droplet forming the fine droplets from the liquid bulk. So it would be very important if we were looking at the atomization, but because we're only looking at the flow within the needle, it isn't as important, but we have inputted surface tension values in.
So the model takes to the point of sort of aerosolization then just before?
Just before that, yes. So the fluid flow before the fluid exits the nozzle.
Brilliant, thank you.
Well, are there any further questions from the floor? Otherwise, maybe I can ask you a question, because you showed the simulation based on this 50% PEG formulation, which is probably an artificially high viscous formulation. What would you estimate to be like the typical viscosities of formulations? What have you seen, or what are you working on in aside of the simulation?
So currently the nasal formulations that we are able to spray with the traditional and sort of newer nasal spray pumps are very low viscosity. They're usually 1 or 2% aerosol formulations, which are in the region of about 0.01 Pascal second, I would say, so 10 times more viscous than water. We could improve the mucoadhesion if we go higher, but before this we weren't able to because we would form a jet and not a spray. But from these results, we can see that with nasodose, we're actually able to spray formulations that are 900 times more viscous than water, and that could potentially significantly improve that mucoadhesion in the nose. And we can use more Avicel or any other polymer, really. So yeah, at the moment it's very limited, but we're hoping that it can go up and improve the retention time.
Okay, then thank you again for this great talk.
Thanks a lot. Thank you.